Bismillahirrahmanirrahim. Assalamu alaikum. Dear students, welcome to lecture 9 Control Systems and AI, where we'll be basically discussing about fuzzy logic, a specific field of AI dealing with uncertainty and situations where things are not clear. In this particular lecture, we'll be talking about introduction to fuzzy logic in section 9.1. Then we'll talk about control systems and AI and how fuzzy logic fits in terms of control systems. For example, air conditioners and fridges and room temperature control, etc. Then we'll talk about what fuzzy logic really is and what are the main components of fuzzy logic in section 9.3. And finally, we'll work with the applications of fuzzy logic. And in that case, we'll particularly take an example of a room cooler and apply fuzzy logic and see how fuzzy logic works and how the temperature control mechanism actually happens. So that is the list of topics for section 9, lecture 9, and I hope you enjoy it. This is the last lecture of soft computing and the last main topic, let's say, in soft computing, and I hope you have learned a lot about the main topics of AI during the course of soft computing, Intro to Soft Computing, CS352. Okay, so this is a new topic that we're going to discuss in this particular lecture, in this particular section. We'll be talking about the fuzzy logic, which is specifically applied in cases where the input is not so well defined, or for example, the system is a control system. Anyway, those are the topics probably for the next few lectures, but in this particular section I'll be talking about first introducing you to the concepts of fuzzy logic. What does the fuzzy logic concept mean, what it's the definition of the term fuzzy logic itself, and the other basic introductory stuff. This will be followed by examples from real life of how fuzzy logic works. Then I'll talk about differences between the traditional logic and the fuzzy logic, and kind of give examples of both, or maybe to kind of define the characteristics of both. This will then be followed by the 3 steps of that are being followed in a typical fuzzy logic system. The first step is fuzzification, where the crisp input is converted into a fuzzy input, let's say. Then the second step is inference, where we use the database and rules to define the to basically infer and process the fuzzy input from step 1. And finally, in step 3, we convert this fuzzy output that we get from the inference step to the crisp output, and that crisp output could then be used to dictate the system, like what is the result of our inference. And then I'll talk about the potentials of fuzzy logic, basically applications, and specifically I'll be talking about control systems and the way they work. And this will finally be followed by the summary of the whole talk, where I'll be presenting the key points from section 9.1. So what is fuzzy logic? If we go and look at the meaning of the word fuzzy, the word fuzzy refers to things which are not clear, which are basically vague, which have some degree of uncertainty in them, which are not absolutely to the point. Let's put it like that. So that's what the word fuzzy means. But when we define the term fuzzy logic for AI and AI related systems, we define it as any event or process or function that is changing continuously and cannot always be defined as either true or false. That is, it cannot be defined by Boolean logic, which means that we need to define such activities in a fuzzy manner with a degree of let's say if you want to understand this definition clearly, it would basically be like if you're trying to define gray. Well, the color gray is different from black and white. It's somewhere in between. It has some shades of both white and some shades of black. So this some shades term which I'm using is kind of fuzzy. So that those shades etc. define the fuzzy logic. And in this case, the color gray represents a particular event or a process which is a combination of two or more binary processes. In this case, this is black and white, are two unique events. They are basically Boolean events, and when you combine them, you can basically form some degree, some shades, some new let's say mixture, and this mixture is basically the result of combining black and white. The good thing about fuzzy logic is that it resembles the human decision making methodology. We typically don't think of the computers typically think of events and objects etc. in terms of Boolean logic, and that's why the whole language is basically Boolean, the computer language. But if you think of humans, we don't really think in Booleans. We usually have we usually cannot directly classify each object into a distinct class. We usually place it as a partial member of both classes, or maybe more than two classes even. So this partial membership thing is kind of what we do, and this is exactly the same as will be done in the membership function of fuzzy logic, as you're going to see in probably in the next section 9.2, where I'll be talking about fuzzy sets. Of course, when I talk about some degree or partial membership, this actually means that there is something that is vague, that is not clear, and the information that we are getting from the system is imprecise. It's not perfectly good enough for us to classify that object into only a one specific class. It might belong to different multiple classes at the same time. For you, I think it would be simply to say that this is basically just a gross oversimplification of the real world problem, and based on the degrees of truth rather than the usual true or false values or 1 or 0 values, just like you have seen in Boolean logic and discrete mathematics. So it's kind of a the problem is that you cannot clearly classify it into one of the two groups. The object that we're trying to classify partially belongs to both the classes or all the classes. So with that thing in mind, I think we can clearly move on to what is fuzzy logic, and let's see it by example, and let's see its history. So what is fuzzy logic? Well, to define fuzzy logic, I'll first need to define what is traditional logic and what is Boolean logic. In Boolean logic, you always have two classes. You can either true or false. In case you are true, you assign the class value 1. In case you are false, you assign a class value 0 to the object. But in fuzzy logic, it basically defines each object in terms of partial memberships of both classes. The object can be true and false at the same time. The degree of belonging to a particular class, or the truth value as we call it, is basically 0.7 for true and 0.3 for false. So you're more inclined towards truth or true class, but you also have some shades of false class. If I go by a typical example here that I really need to give. So the question here is Riaz honest? If I use Boolean logic, if Riaz is honest, then it's true, and the answer is yes, it could be 1, he belongs to class 1. If the answer is false, he is not honest, then it's basically the answer is 0. So in Boolean logic, you have exactly one answer. You cannot belong to both the answers. But if we think of fuzzy logic, the same question can be answered in different manners. So is Riaz honest? The same question is asked to a fuzzy system, and the fuzzy system can answer extremely honest, basically kind of saying that Riaz gets 1 or yes or true, perfectly only belongs to that class, for example. Or the other way could be that the system classifies Riaz as very honest. He's honest 85% of the time, and let's say 15% of the time he can be dishonest as well, or belong to another class. I don't necessarily mean dishonest, but it could be that we don't know, or 15% of the time we don't have enough data, or whatever. So for 85% of the time we know that he's honest. Similarly, the answer could be somewhat honest or sometimes honest, and this time we can say that he's honest 35% of the time, and for 65% of the time he belongs to some other class other than honest. And finally, we can basically say that Riaz is extremely dishonest. In this case, we say that it's like there's a 0% chance of all the cases that we have seen, he never ever actually has been honest throughout. So this is somewhat different, and in this regard I would say that the fuzzy logic differs in the fundamental behavior and the fundamental definition from the traditional or Boolean logic. And just to talk about a little bit about its history, fuzzy logic is basically introduced by Lofty-e-Zadeh in his research paper Fuzzy Sets in 1965, and we consider this person, the person on your screen, and that you can see that paper actually in which he proposed fuzzy logic. This guy is considered to be the father of fuzzy logic, and I really need to quote a sentence from that he has used in his paper, and where he says that fuzzy logic is not logic that is fuzzy, but logic that is used to describe fuzziness. So it's not a logic that is fuzzy. You're not going to use rules, etc., and stuff that makes things fuzzy, but instead you're going to define through logic systems that are fuzzy. So it's used to define fuzzy systems, and the fuzzy logic is the logic behind fuzzy systems. And of course, fuzzy logic is fantastic as it solves complex problems using simple rules, and we'll see how that works. But first, I think we need to start off with a few examples. So let's take the first example of a tap water temperature. How to define the temperature of a tap water? That's a simple question. If you use traditional logic, you're just going to say that the water is cold or the water is hot. But if you use fuzzy logic, you're going to give up a degree of coldness or a degree of hotness. So for example, as you can see in the picture, for using traditional logic, we either say that the water is cold, in that case it is indicated by blue, or we say that the water is hot, in which case it is indicated by red. And as you can see, there's no common region between them. It's basically like saying that you are red, and in that case you're extremely red, or you are blue, and in that case you are extremely blue. But when you talk about fuzzy logic, the same tap water temperature can be represented as a degree of coldness and hotness. So it would, if we go in between the region, you can see that on the extreme right and on the extreme left, the water is cold or the water is hot. But in between, the water can be normal, it can be somewhat cold, it can be somewhat hot, or some other degree, whatever you want to define it and whatever you want to name it. But the region in between, you can see that the color is somewhat white, and that white region is indicating that this is right in between cold and hot. So in fuzzy logic, you have got a degree of belonging to both the classes, and that is the main difference between the traditional logic and between the fuzzy logic. So the second example that I'm going to give you over here would be that of automatic braking system. So let's just suppose that we're using traditional logic to perform this task. We have two cars that are going on a road, and the basic question is, the car at the back is using the traditional logic to define what it has to do. If it is too close, it is going to apply brakes. If it is far off, it's not going to apply brakes, and continue to accelerate and cover the distance between both the cars. So the question here is, if car is closed, well, the answer can be yes or no. In case it is yes, we assign a value 1 to it, otherwise we assign a value 0 to it. Based on the question, if the car is closed or not, the answer is basically in the form of should brakes be applied or not. So when brakes are on, the result is 1 for brakes, and when they are off, the result is 0 for brakes. So there are two scenarios now. When the car is closed, you should actually apply brakes. When the car is not closed, you will not apply brakes. That's a simple scenario in terms of traditional logic. There's nothing in between. So this is what you're going to do. You're going to check, is car closed? If the answer is 0 or no, well, the brake should be 0 or off. If the car is closed and the answer is yes, 1, in that case brake should be on. Brakes, the variable brake should have a value 1. So this is traditional logic. Now think of a scenario, what's going to happen in real life when you apply traditional logic. The car is initially far, so you're not going to apply brakes, you're going to be closer to the front car, and once you enter the range close, you'll immediately apply brakes. But think of it, you're right at the boundary, and immediately as soon as you apply brakes, you'll immediately get out in the far region, and hence you'll release brakes. But as soon as you now release brakes and accelerate, for example, you'll get closer to the car and you'll get into the close range. Again, you'll start applying brakes, and the process is going to continue. It's going to repeat itself, and you can imagine what is happening with the guy or with the people in the car. They're going to basically be going forward, moving back, going forward, moving back, moving like basically a break dance sequence or something. So that is what is going to happen if you use a traditional logic system for an automatic braking system, and it's going to be a terrible experience for all the passengers who are sitting in the car, as well as it will harm the brakes as well. On the other hand, let's try a fuzzy logic system. In fuzzy logic system, the question is the same and the answer variable is also same. So the question is car closed? And the answer would be a range of yes and no. So it would be a number between 0 and 1, and that number actually indicates that how close are we or how far are we. And similarly, the output would be the variable brakes, which would again be a number, but this time the number would be between 0 and 1, and it would be a range between off to on again. So how hard do you want to apply brakes? This number is going to indicate that. A 1 would indicate that apply full brakes, 0.5 might indicate apply half brakes, and 0 might indicate apply no brakes, for example. So let's say that if we are close and we determine that we are close by, let's say, a value of 0.8, which means we are pretty close, then in that case we need to apply brakes at the value of 0.8 as well, and we need to apply a fairly heavy pressure onto the brakes, and brakes need to come out fast. On the other hand, if we are close but not really very close, for example we are at a distance of 0.2, in that case we need to apply slight pressure on the brakes and very light brakes as well. So the distance might still continue to close down, but it won't be really slowed by or applying partial brakes. And the closer we are going to come, we are going to evaluate it at run time and keep increasing pressure. Or if we are going away from further away from the main car, we are going to slowly decrease the pressure on the brakes. And this particular example is a specific example of or typical example of a fuzzy logic system. So from both the examples that we have seen here, what is the difference between a fuzzy controller and a traditional controller? I have noted out 4 major differences, and you can kind of see them and go behind the logic behind each one. The first main difference is that the traditional controllers need to know detailed physical properties of the system. While the fuzzy logic controllers do not need much detailed knowledge of the system, what the controller should do is determined by linguistic rules, and rules are the ones that define the behavior of a fuzzy logic controller. In case of traditional controllers, you need to get the exact physical property and you need to define it, and based on the physical property you actually come up with the reaction of the traditional controller. Will brakes be applied or not be applied depends on the exact value of how close you are. On the other hand, in case of fuzzy logic controllers, you just need a degree of membership of how close you are. You really don't need an exact crisp number. You do not exactly need the exact distance between both the cars, and in that case the controller will automatically decide, the system will decide what to do with this knowledge. Okay, so the second difference now between traditional controllers and fuzzy logic controllers is that the traditional controllers are usually depending on systems that are too complex and have to be idealized to develop a traditional controller. So for example, again, the automatic car braking system was really a simple system, but yet I would say that the traditional controller found it too complex to handle, and it really needs to be idealized. It really needs to work perfectly such that whenever we are close, we are really close, and when we are far, we are really far. If that is the case, of course the traditional controllers are going to work absolutely fine, because full brakes on should be the case if we are really close to the front car, and similarly no brakes on should always be the case if you are too far away from the front car. On the other hand, the fuzzy logic controller, in case of those, the system does not need to be idealized to develop a working fuzzy logic controller. Like I said, you could be somewhat close, you could be somewhat far, and in that case no full brakes will either be applied or they will not be completely left off. Some slight pressure or more pressure might be applied, and in that case fuzzy logic actually appears to be the major difference maker. Okay, moving on to the third case or third difference. The traditional controllers do not have a full representation of the system, or do not really represent the full system, I should say, and they are only representing the reduced part of it. On the other hand, in case of fuzzy logic controllers, we can actually have the full representation with each and every variety and each and every case well defined. So for example, let's say if you want to understand this difference, let's say that in case of a traditional controller, all you need to do is you need to define the boolean value or the class that a particular event belongs to based on its exact number, but you do not define each and every scenario. You not define that what happens if the number is negative, what happens if the number is positive, what happens when the number is 0, what happens when the number crosses 100, or any other legal boundary. So you might not define it. In case of fuzzy logic, you have to define each and every single possibility that may occur to the input. So in that case, you really need to be representing the full system. You might not need a reduced, or you might not work even at times with a reduced representation. So that's the third major difference. Okay, and finally, the conditions when traditional controllers will work are usually fairly limited. So you need to place limitations. Like I said, in the case of car example, you are either very close, or basically you are very far. If that is the idealized case, that's a limited condition that will most probably that does occur, of course, but it's not the most common condition. On the other hand, the conditions when fuzzy logic controllers will work are much more robust, and it works absolutely fine for a variety of conditions, and not limited conditions like is in the case of traditional controller. So in that case, you can be somewhat close, somewhat far, very close, whatever. So there is a range of these things, and all these ranges do occur. And the thing is, the fuzzy logic controller will have a a logical response to these cases, unlike the traditional controllers. So these are the four major differences that I see between traditional controllers and between fuzzy logic controllers. Okay, so now I really want to introduce you to the concept of fuzzy logic and how does fuzzy logic really work. And in this case, this is just a small example. We'll see the detailed working actually in the I think section 9.3 and 9.4. Mainly when we see the water cooler example, there is the whole detail. But for now, you just need to get a hint of what's going on. So we take a very simple example of a very intelligent robot. I've named this robot Inam, and this robot basically works for boiling an egg, and it uses fuzzy logic. So Inam is a robot that can boil an egg, and it uses fuzzy logic for boiling it. So okay, boiling an egg appears to be a very trivial task to most of you. However, I think only a few have mastered the art of preparing the perfectly soft boiled egg. You don't really want it to be too hard, you don't want it to be too soft and squishy. So you want it to be right there in the zone, and you want to have the perfect soft boiled egg. Well, the traditional recipe, I would say, would be that Inam has found and that he can use is that he can drop the egg in hot boiling water and remove after 5 minutes on the clock. So that's the traditional recipe that Inam has found, and Inam is using this particular recipe to boil eggs. Unfortunately for Inam and for us, the egg sometimes it turns either too soft or it turns too hard, and this is a lot troubling for us. Like if we boil it for 5 minutes, we never happen to get the perfect soft boiled egg. And the issue that Inam has realized is that he has been told that by the human master chef Uzair that the egg size should be considered when deciding the boiling time of the egg. So there are two rules that Chef Uzair has told Inam. The first rule is that if the egg size is small, then boil for less than 5 minutes, and if the egg size is large, then boil for more than 5 minutes. So that is the advice from Chef Uzair, and he's very right in saying that the egg size should be looked at before you start boiling an egg, and instead of just boiling it for 5 minutes, you should increase the duration if it's a large egg, and if it's a small egg, then you should basically reduce the duration from 5 minutes to less than 5 minutes. But well, the words from Master Chef Uzair have actually confused our robot Inam. What's the confusion? The confusion is, what does the words small, large, less or more mean in both the rules? Well, the answer to that is, you take an egg and you weigh it out. So this is how we're going to quantify the qualitative terms in the rules into quantitative terms. And when I talk about small and large, it actually means that eggs usually weigh between 40 grams and 70 grams. So 40 grams is basically small and 70 grams is large. Anything in between is basically a function of both. Then we can look at the boiling times, which range between 3 minutes and 6 minutes, and that defines the less and more. So the less means boil it up to 3 minutes, and more means boil it up to 6 minutes. And this information, which is actually kind of converting or qualitative information, small, large, less, more, into quantitative, 40 grams and 70 grams, 3 minutes and 6 minutes. That's the quantitative information. Fuzzy logic utilizes this knowledge. So designing the intelligent egg boiling robot in ARM requires 3 main steps. The first is fuzzification, second is inference, and finally we talk about defuzzification. We'll use the robot example here and we'll kind of see the 3 steps just to get you started with what is fuzzy logic and how fuzzy logic works. So here's the first step that an arm or robot is going to perform. He's going to take the egg and measure its weight. According to fuzzy logic, any egg is both small and large but to different degrees. For example, Inam considers 50 gram egg as small in a larger degree and large in a smaller degree. So these are called fuzzy values. Degree membership to a particular class, these are called fuzzy values. And what Inam does is that he is basically going to start weighing an egg, and that egg weighs to 50 grams. So he classifies it as 70% belonging to the smaller class and 30% to the larger class. Since the egg is both small and large but to different degrees, Inam now applies the 2 rules but again in different degrees. So if you remember, the 2 rules are: if the egg is small, then boil for less than 5 minutes. If the egg is large, then boil for more than 5 minutes. So since his egg is 70% small, he is going to go for 70% less than 5 minutes. And since it's 30% large, he is going to go for 30 minutes more than 5 minutes. And he can come up with some sort of a number that defines his exact boiling time. But for now, what he has defined is that he needs to boil it 70% less than 5 minutes and 30% more than 5 minutes. That is his results. That is his inference from step 2. So just to clarify maybe one more point, the inference in the previous step was actually based on rules. Whatever rules you have, you're going to define your inference on that. And since he had basically inferred that it's 70% less than 5 minutes and 30% more than 5 minutes, so he's going to the robot Inam is now going to calculate the actual boiling time based on the fuzzy values in the previous step. And hence, for the 70% less and 30% more than 5 minutes, a balanced decision would be to boil the eggs for approximately 4 minutes. And that is the exact boiling time that Inam comes to the conclusion, and that's what he's going to do to get the perfectly soft boiled egg for a 50 gram for an egg weighing 50 grams. So what are the potential applications of fuzzy logic? After we have seen the typical example and the 3 main steps involved in the fuzzy logic systems, we can say that fuzzy logic is used in a lot of different control systems. And the examples here can be of kitchen appliances. For example, in your microcontroller based microwave ovens or basic ovens. It can be used in car control systems like we have seen for the braking system, automatic braking system. It can be used in aerospace vehicle control systems. It can be used in washing machines. It can be used even in camera stabilization systems where for example, you want to record something in the air or something and you want to keep the camera stabilized. It has been extensively used in that scenario as well. So while fuzzy logic has been practically used in a lot of practical applications, in particular related to control systems, it can also be used in other theoretical applications as well. And for example, it can be used in image processing and identifying objects in images. It can be used in decision making, for example, stock exchanges and other stuff. It can be used in route planning. So if you want to go from one place to another, which route suits you the best and for a given set of constraints, it is being tested at the moment for safety critical systems. And we have recently had a aircraft crash where maybe fuzzy logic could have helped us save or warn or something. And finally, it can be used for it is currently being used for small satellite altitude control and controlling them maintain their altitude on the surface of Earth beyond in space beyond a certain limits. So fuzzy logic has a lot of different applications in various fields. In terms of practical life, I think the main applications still at the moment are in control systems and in all form of control systems. But it has found its niche even in image processing and decision making, route planning, and other applications and fields. Okay, now let us discuss the summary or the key points of lectures 9.1, section 9.1. First of all, fuzzy logic was defined in 1965 by Lotfi-e-Zadeh, and he defined it as he basically says that it is logic that defines fuzzy systems and not fuzzy logic that defines systems on like the other case. The fuzzy logic has found a plethora of applications, in particular in control systems as well as in other normal applications as well. In fact, sky is not the limit when you start defining applications for control systems. The fuzzy logic differs from the traditional logic in four main categories, and we discussed those four categories during this lecture. We saw an example. We saw actually 3 or 4 examples, but a specific example that where I used fuzzy logic rules and fuzzy logic inference methods, etc. We saw the example of Inam the robot boiling and preparing the perfect soft-boiled egg using fuzzy logic. We saw that in that particular example, we saw that systems that are based on fuzzy logic have 3 main steps. The first step is fuzzification of the crisp input to the system. The second step is inferring the making use of rules, fuzzy rules to make inferences, and finally defuzzifying or defuzzification of fuzzy inferred values that are inferred from in the second step and converting them to crisp output or exact values that are required. So in this case, for example, it was the exact time that we required, and we inferred it from 70% less and 30% more, etc. So we inferred it and we defuzzified that fuzzy value into a crisp value of exact 4 minutes. So with that, the section 9.1 comes to an end. We'll be continuing on with the topic of fuzzy sets, specifically in the second lecture, and I'll continue I'll take on from differences between the terms crisp and the term fuzzy, etc. in the next lecture as well. So have a good night and a good day, and hope you have learned something about fuzzy logic. This is a very interesting topic and worth learning, I think, for all of you. Thank you. Bye bye.